Let's take a look at a boiling point problem. At first glance, it appears this problem does not provide enough information to solve the problem. However, there's some information that we know that's not provided in the problem. That would be that we know the boiling point of water at 1 atmospheric condition is 100 degrees Celsius. This gives us two data points, a temperature and a pressure, which we can utilize in the Clausius-Clapeyron equation. The Clausius-Clapeyron equation requires two pairs of pressure and temperature data. The heat of vaporization for water and the R constant are all necessary. Because we know that the temperature that water boils at is 100 degrees Celsius, that can be a T1 value. P1 then becomes 1 atmosphere pressure, or let's use 760 millimeters mercury. Reason we can use these is that the vapor pressure of water is equal to the outside pressure, or 1 atmosphere, at the temperature at which boiling occurs. Normal boiling point is 1 atmosphere, or 760 millimeters mercury, so the vapor pressure of water when it's boiling under 1 atmosphere conditions is 760 millimeters mercury. The temperature when the vapor pressure is 760 millimeters mercury is 100 degrees Celsius, which is the same as 373 Kelvin. So we have our T1 and P1 data. The other data points, our T2 is what we're looking for. That's our unknown. Our P2 would be the pressure that we have at the peak of Mount Everest, which is 253 millimeters mercury. Now, at the peak of Mount Everest, also, the boiling point would be the temperature at which the vapor pressure becomes equal to the outside pressure. So we're looking for the temperature when the vapor pressure, P2, becomes equal to the pressure in the air on the peak of Mount Everest, which is 250 millimeters mercury. Other information we need to solve the problem would be the heat of vaporization of water, which we have as 42,700 joules per mole, and also our R value from the gas constant, which, because we're doing an energy-related calculation, we need to have units that include energy, which in this case is the joule. The unit of measure for energy has to be part of our R value that we select. Putting all the information into the Clausius-Clapeyron equation gives us ln P2 over P1, which would be 253 over 760. We have our delta H VAP, 42,700, our R value of 8.31. T2 is what we're looking for, so that remains as T2. Our T1 value was 373 Kelvin. Our first step would be, let's simplify some of our numbers. Let's find out what the natural log is of 253 divided by 760. Let's also find out what 42,700 divided by 8.31 equals. This brings us to this point where we have negative 1.100 is equal to 5,138.4 times T2 minus 373 divided by T2 times 373. Continuing to try to isolate T2, let's divide out by 5,138, and that will lead us to the next part as we try to simplify our equation. That brings us to negative 0.00214 as T2 minus 373 divided by T2 times 373. Let's multiply both sides by T2 373 as we continue to try to isolate the T2 expression. This leads us to this expression. Now we're going to simplify by multiplying through by 373. This brings us to this point. We now have negative 0.0798 T2 is equal to T2 minus 373. Let's add 373 to both sides to end up moving the 373 to the left side of the equation. We've now moved the 373 to the left side. What we can now do is take the negative 0.0798 T2, take that to the right side to further combine and get our T2 on one side of the equation. This brings us to this point. 373 is T2 plus 0.0798 T2 we'll combine our T2 expressions. Now that we've combined the T2 expressions, we have 373 equals 1.0798 T2. We can divide by 1.0798 to isolate the T2. This brings us to this point in our calculation. If we divide this through, we end up with 345 Kelvin is equal to T2, which converts to 72 degrees Celsius will be our T2, and this would represent the boiling point of water on the peak of Mount Everest. Now, this particular type of problem can be used for any calculation with a boiling point as long as we have two sets of vapor pressure and temperature data. Sometimes it looks like we may not have enough information, but the reality is we know that water, for example, boils at 100 degrees when its vapor pressure is equal to 1 atmosphere.